Okay, Vlad, do you want to get it started?
Yeah, I think so. Okay. Hi, everybody, and welcome to the CMAS session on modeling to support exposure in health studies and community scale applications. I'm Vlad Isakov from the US EPA Office of Research and Development, and my co-chair is Amir Hakami from the Carleton University, Canada. So we have 14 presentations in this session, and we try to summarize it, but it's a real challenge because we have such a wide spectrum of different modeling approaches used to support exposure in health studies. And spatial scales range from regional to urban to community. So what we wanted to do, instead of us trying to summarize the findings from all the presenters, we would like everybody in this session to give about 2-minute summary and highlight the key findings, main conclusions, and then the rest of the time, we will spend to answer the questions. So officially, we have only 2 questions submitted prior to the conference. So I want to ask Amir, do you want anything to add to this? Or?
No, I think I'm good.
Okay, all right. So the first presenter is Jacob Becker. Okay, his title is Mapping Yearly Global Surface Ozone Through Regionalized Air Quality Model Performance Corrections and Biasing Maximum Entropy of Observations and Model Output from 1990 to 2017. All right.
Hey, can you hear me?
Yep.
So you're looking for a 2-minute summary? There's obviously more in the presentation online, but basically the purpose of my work is to combine station observations with models. So station observations, as we all know, are accurate, great, but only in a few distinct areas, whereas the models are great because they cover a wide area, but we know have some biases. So essentially, we have a 2-step process to try and correct the biases in the model. And first step we do is we sort of we create this one model, which is just through the work of Kailan. I can't take credit for that. Kailan Chang. He created one model out of a bunch with some bias correction. And then we did another step where we sort of looked in the very local trends, comparing the model with the nearest observation points around it, looked at the trends there, whether it overpredicted, underpredicted, and whether it overpredicted high, underpredicted low, which tended to be what we saw. Based on those specific local trends, we'd then correct this model. We then use that model as the background in Bayesian maximum entropy, which is where the data fusion happens. And essentially what that does is it corrects when you're near an observation, it'll correct to that observation. And the farther away you are from an observation, the less influence an observation has. So if you're close by, you'll get some influence from an observation and then rely more on the model. And the farther away, the more on the model you rely. And that creates a single smooth surface. It's able to correct over space and time, which is a great feature for the areas we get data for later, but don't have it initially. And we found that it created a more accurate global model of ozone pollution from 1990 to 2017. The original impetus for this project was for the global burden of disease study.
And we have 2 questions submitted. These are the only 2 questions in this session. In this whole year. Okay.
Great. Yeah. So the first question is the question that is the real question, because it's sort of hard to validate the model where we don't have observations. Like we have no real way of cross-validating it in areas where we don't have any observations. So we tried to simulate that. And if you look at the presentation, that's what the last couple slides cover, the checkerboard cross-validation. I didn't explain it too much in depth in the presentation, but essentially what we do is we sort of simulate a data sparse region by choosing a large square, eliminating all the data in it when we feed it into our model, and then estimating at those points in the square. So it's not able to use any of the information within that square. It's just using the corrected model that we created earlier, plus if it's close enough to observations that are, maybe like on the edge of that box we create, it might get some influence, but overall it'll mainly be relying on the model. And we did find that it did have, you know, it performed better than the plain models did, or the model Mead did. But, you know, we can't say for sure in areas which are completely far away, because as I noted, you know, if you're, our correction relies on you being close enough to data points to trust that the trends in the model there represent the area. So especially in like China and South America and Africa, we just don't have any close model points to weigh the model. So it's based on, you know, only a few points, the corrections to the model there, and we really have no way of validating it without more observations. And then as to the second question, can you comment on the performance fusion with the worst ozone monitors? So we used the TOR and CMAC, or not CMAC, sorry, what is the actual acronym for it? CNMC, I think. Yeah, CNEMC. So we used TOR, and that's the China National Environmental Monitoring Center. TOR is the Tropospheric Ozone Assessment Report. So we use that as our monitors, which they did a pretty thorough validation of those monitors before putting them in. So we don't actually have anything that takes into account whether or not the monitors are accurate or not. We take every single monitor point as if it's accurate, because it's the best estimate we have. So there's lots of quality control that goes into both these products, and we essentially trust that, as we had no better sources, and we trusted that they would have thrown out, and we did see that they did throw out some monitors that you know, were less accurate. So we, in terms of the ramp weight, we trusted them all completely, but we didn't, you know, invalidate any of them.
Thank you, Jacob. And now we'll move to another one. So I think this is Martin, right? So let me go to the one slide summary you sent me. Okay. Yes, yes.
Okay, thank you. Well, first of all, thank you very much for inviting us. Us, when I say us, it's because the presentation was created today by my colleague Gulnush Bizani. She was not available today to do this presentation, so I will be doing that instead. We did the study together. My name is Martin Gauthier. I'm working for RWDI, which is a consulting company in Ottawa. My office is Ottawa, Canada. What I will be presenting today is a project where my client was the Peel Public Health Department, and it's related to the off-peak delivery emission scenario. So just maybe a little bit of background for the presentation. We have used WRF Smoke CMAC at a very high resolution of 1 kilometer. We create a base case. It's all based on 2015 emission inventory from Canada and 2015 metrology. We did a full year, and our mainly focus is the Greater Toronto area in the Peel region, which is just west of Toronto. This region included a lot of distribution center, and also obviously the Toronto Pearson Airport, which is the biggest airport in Canada. So this off-peak delivery scenario, it's a scenario where we remove all the emission from delivery of retail trucks, happening between 7 a.m. and 7 p.m. and we put those emissions out in the evening and overnight. And basically why we did that is because this region of Peel, they had a pilot project where they really assess what could it be, what could happen if they would go with a scenario like that. What I mean by that is they had trucks. So they pinpoint some facility or some location, some store, and that participated to this pilot study in summer 2019. And basically what they have done is they track all the number, the time they spend in the truck, the number of stops, the speed, and all this information that can be after the study could be integrated into an emission model like moves and estimated the emission, and it was found that the emission reduction was 11%. But before they go ahead with implementing this kind of way of delivering the goods, they wanted to know if the impact on air quality, and this is where we with CMAC we did the modeling. So maybe just very quickly mentioning a few assumptions that we had in the model. Obviously, it's not we only pinpoint the retail delivery because this is the pilot project only focus on that. Retail delivery, it's 43% of light truck, represent the emission of 43% of the light truck and 17% of the medium and heavy trucks. And what I should say about that, it's we applied the off-peak delivery scenario to not only weekdays but also weekend. We model on we had to do the modeling only on two months of the year. Like we've selected August and March, one in winter, one in summer. And obviously, what we applied this emission scenario only inside the region of Peel. So everything outside the region of Peel was the same as the base case. So the findings very quickly, maybe. I could say that overall, it's not a big reduction in emission. It represents, when you assess this scenario, it's only between, depending on the pollutant we're looking at, it's an overall reduction of 3 to 7% reduction of the overall emission in the Peel region. By modeling that with CMAC, we realized that it was really hard by looking at ozone and PM2.5, what would be the real impact on health. So what we ended up to do is to look at the air quality health index in Canada. And we kind of assessed that. And we realized that overall, I would say that there was a slight increase in the number of high-risk air quality hours at some specific location, but it was not critical. Those locations were mostly close to roads and not necessarily tied to populated areas, so that's a good thing. And one of maybe the key, my end message is why that would be the case. It seems to be a bit the opposite that we were expecting, but actually, when you think about that, by putting the emission at the specific period, such as the transition period of sunset, sunrise. We all know that the dispersion is a bit weaker for those periods, and that's probably why we have at some specific time higher concentration and some increase in high risk air quality hours. So
Thank you.
Pretty much it. Thank you.
Yeah. All right. Very nice summary. So let's move on for the interest of time. The next speaker is Dr. Mike Breen. All right, Mike.
All right, can you all hear me?
Yep.
Okay, so I'm gonna, so my presentation talks about how we integrated the CMAC model into a smartphone app that we've developed called Track My Air. And the app models individual level exposures to both ambient PM2.5 and ozone. And you can see in the slide where for inputs into the exposure model, it can pull in besides CMAC and also pulls in the measured concentrations from either AirNow for both PM and ozone. It can also access in real time the purple air data from low cost sensors, purple air sensors for PM2.5. And specifically for this audience, we're looking at showing the capability, the new capability of now inputting model predictions from CMAC. You can see this is version 5.1, getting both PM and ozone. So the features that the app actually accounts for is so it knows where the user's location is based on the app, and it obtains the input information from the nearest PM 2.5 or ozone monitor in the case of AirNow or Purple Air, or the nearest CMAC receptor. And then it accounts for the variability of how much attenuation for example, different buildings such as your home does. So it has an air exchange rate model that is one parameter inside the infiltration model for homes. And it also accounts for the driving forces for the air exchange rate, which is indoor-outdoor temperature differences and wind speed. So it needs the weather data that it pulls automatically from the nearest weather station. It also accounts for changes in infiltration due to open windows and people operating window fans. It also accounts for the removal of PM 2.5 if you're operating a home air cleaner. And what our latest feature also basically tracks the geolocation of the person using the smartphone, and then applies a model to determine when the person is indoors or outdoors. And when they're indoors in different locations, it applies the appropriate infiltration factor at that moment which is time matched with the PM ozone concentration. So you can get a personal exposure this way. It also, we're using now wearable fitness devices such as Apple Watch. And using that, it can account for your physical activity. And we use this then with a model to determine inhaled dose. And we're basically designing it for non-technical users. So we've applied it for epi studies with the nurses actually running it. So here's kind of a screenshot showing you the inputs once again for the model. We talked about that where we have the low-cost Purple Air sensors, AirNow. And this is a screenshot of the app called Track My Air. Basically, you tap on that Calculate Exposures button, and if we're running CMAC, it takes about 30 seconds. It'll actually calculate your past 24-hour average PM 2.5 and ozone exposures and dose. So that's the capability of the app, and it gives you daily 1-hour averages also. And I think, is that my last slide?
Yeah.
Okay. Yep. So that's a high-level overview of the app.
Thank you, Mike. Yeah. So that was a great overview. Great summary. So I would encourage everyone who is watching this basically to submit questions if you have any questions through the Q&A, and we will have time at the end of the session maybe to address it. All right. So the next presenter is Emma Dumbo. So I will turn it to Emma.
Thanks, Vlad. So our work is looking at using CMAC PFAS development for predicting the fate and transport of per and polyfluoroalkyl substances, or PFAS, in the atmosphere. Do you have my next slide? Thank you. So we kind of developed a new state-of-the-science model that we're calling CMAC PFAS. So we just added 26 explicit PFAS into CMAC and lumped another 24 PFAS into a representative species. And we compared the deposition of one PFAS, which is Gen X and is of particular concern in North Carolina. The deposition was measured by North Carolina DEQ, shown in pink on the X's on the right, and our base model is in green, and that's what we primarily talk about in the talk. You can see that the model does a fairly good job. The second conclusion of our talk was that about 95% of emissions are transported greater than 150 kilometers downwind, and that's our model domain size is about 150 kilometers from the facility that we're looking at. So about 95% of emissions are transported outside of our domain. And then finally, we found that including chemistry and dynamic partitioning is really vital for capturing the correct atmospheric behavior. So that's really why we use CMAC, is that it's able to simulate dynamic partitioning and chemistry. And so what we're showing on the right is the deposition in grams per day within the domain for two different compounds that are structurally very similar and just differ in one functional group. And you can see that that has a huge implication for not only the processes of the removal processes, but also the total deposition. And I will leave it at that. I'm happy to take any questions.
All right, thank you. So yeah, if there are any questions at the end of this session, we might, be able to answer them. All right, so the next speaker is Changping Kuo, right?
Yep.
I will turn it to you.
Thanks for that. Yeah, basically my research is focused on the heterogeneity of the burden of disease at a diverse urbanization level. And our motivation is that we observe that there are different risk values between urban and rural areas. But when we calculate the national burden of disease estimation, we always use the same risk values over urban and risk area. And we develop a framework in terms of the 6 databases, including hospital admission data, monitoring data, CMAC data, emission data, and land use data, and population data to calculate the to estimate the burden of disease at final spatial resolution. So first of all, we build up the exposure risk map based on the hospital data and the monitoring data, also land use data. We also develop a urbanization level index to evaluate the risk between the different urbanization level region, including the urban and rural areas. And we also found that we have there are some trends where the risk vary with the urbanization level. Like we found out that the death risk is higher in rural areas, but the cardiovascular disease risk is higher in urban areas. There are some factors to affect this trend, like medical resource accessibility or individual factors, or the PM2.5 toxicity between these areas. And also we also build out the daily concentration map, like we fuse the CMAC data and air quality monitoring data to build up the daily concentration map. And then we also do the population distribution map. So we can build up the overall the whole burden of disease map with the 1 kilometer by 1 kilometer resolution. And we also do another uncertainty analysis, like we use a USP recommend risk, and we use average risk and the graded risk we build. And also we use the monitoring data and the CMAC data to compare the burden of disease result between these scenarios. So we also found out there are some underestimation and overestimation between rural and urban areas. So if you want to look at the details, you can read my videos. Yes.
Thank you, Champion. All right. So the next speaker is Dr. James Keeling from USCPA.
Thanks, Vlad. Yeah, so we used multiple models to characterize PM2.5 concentrations and exposure. Specifically, we looked at 9 models, first 2 chemical transport models, CMAC and CAMAX, and then 7 non-CTMs that were kind of statistical models that were fit to the monitoring data. So these could range from simple interpolation models to some of the most advanced data-rich machine learning type algorithms. So we took these 9 models and characterized concentrations of PM2.5 in 2011. And we found that all the models did a good job of providing us information of how PM is distributed over the US with higher values in the East and some in California. But the different models had sort of a different spatial texture. Some were smoother, some not so smooth. And we found relatively large differences between the models in parts of the Western US that were kind of sparsely populated and there's less monitoring. Also, if we zoomed into urban areas around the US, we found that the spatial patterns of PM over the urban areas don't really agree among the models. All the models know there's a city there, but the spatial variability differs. This wasn't surprising to us because these large models get fit to national and larger scale data sets. So you don't expect each city or grid cell to agree, but it's an important conclusion as people think about how to apply these methods in the future. Then after looking at 2011 concentrations, we projected those to 2028 using CMAS modeling of some emission reductions. And not surprisingly, we found reductions in PM2.5 due to SO2 emission reductions of like greater than 3 micrograms per meter cubed over broader parts of the East. There was more agreement among the models in terms of the change in PM because we use a single model to do the air quality projection or create the RRFs. So then after looking at the 2028 concentrations, we did some work on exposure characterization. And probably the biggest conclusion there is that we found that the gap in exposure between the highest exposed racial and ethnic group and the least exposed racial and ethnic group, we projected that that gap will decrease as you go from 2011 to 2028. So there's a historical trend of as PM concentrations are being reduced in the last 2 to 3 decades in the US, the gap, the distribution is compressing. So the gap between the least and most exposed groups is decreasing. And we project that that trend will continue into the future, although relative disparities do persist throughout this time. And that's something that we plan to look into further. Thanks.
All right, thank you, Jim. Really nice summary. The next speaker is Brandon Lewis.
All right, hello. Thank you for viewing my presentation. I completed my presentation with my advisor, Dr. Renee Anasia at NC State University. And just to go into a quick short summary of my presentation. So my presentation was based from the HIM3 model, which HIM3, which is the Human Exposure Model version 3, which I think someone will actually talk a little bit more about HIM4, which is the newer version model that is being released. But for my research purposes, I used HIM3, which actually coincides with their air pollution dispersion model, AirMod. And HIM3 with AirMod just allows you to estimate ambient concentrations of air pollutants. So I looked at 2 main pollutants from using my HIM3 model, ammonia and hydrogen sulfide, and I looked at VOCs also. So for my research, I modeled hog farms in Eastern North Carolina, specifically in Duplin County, North Carolina, to model these emissions from these hog farms. And I wanted to estimate exposures just on the vulnerable populations that are actually located in Duplin County. So I looked at kind of these disadvantaged populations to see if they are disproportionately exposed to these pollutants from these concentrated animal feeding operations. I looked at the hog farms that are solely in Duplin County. So there was 483 hog farms that I modeled within HIM3, and also used the National Emissions Inventory that was to 2014 version that's provided also by the EPA. And I quickly want to go into some of my results. I have some estimated ambient concentrations of ammonia and hydrogen sulfide from Duplin County. Ammonia, 6.5 micrograms of estimated annual average ammonia, the max was 51.67 micrograms for ammonia, and the average for hydrogen sulfide, 0.06 micrograms of hydrogen sulfide per meter cube, with the max 0.5 micrograms per meter cube. And this was modeled spatially in Duplin County. So if you go into my presentation, you will actually see kind of the spatial variability of both of these pollutants just throughout Duplin County. And with my findings, I found that the majority of these Duplin counties were located in areas where there are higher proportions of minority and linguistically isolated. Linguistically isolated is basically where you have households where no one over the age of 14 speaks English fluently. So we saw that there were actually more larger clusters of these CAFOs and these larger inventories of hog farms that were located kind of within these communities, and also within communities of lower income. And kind of the main findings just in our research that we see above average exposures of ammonia and hydrogen sulfide for these vulnerable populations, including the linguistically isolated minorities, which includes Hispanic and African-American communities, communities of low income, and communities of low educational attainment. I mean, if you look at my presentation, you'll see just a little bit of how I calculated these disproportionate exposures. Yeah.
Thank you, Brandon. So let me stop sharing my presentation because we're gonna switch to another session co-chair. All right, Amir. Okay.
Okay. Do you want me to?
Or I can continue. You know, either way, you just tell me.
Okay. That's okay. I can do that.
Okay.
And let me just see where we are. I think our next speaker is Dr. Haplopi, right?
Great.
Sorry, Haplopi. I'll get there. Go ahead.
Okay. Hi, I'm Haplopi from the US EPA. I'm a research scientist, and my presentation was on the role of secondary organic aerosol in cardiovascular and respiratory disease mortality in the United States. You can go to the next slide. So we were motivated to do this study because we know that secondary organic aerosol, or SOA, is an increasing fraction of total PM2.5. You can see that in the upper right, where total organic aerosol is one of the major components of PM2.5, and most of that is secondary organic aerosol. And secondary organic aerosol dominates generally at all times of year and in both urban and rural locations over primary organic aerosol. We also noticed that secondary organic aerosol, shown in the bottom right, tends to be high in the southeastern United States, and that's also where cardiorespiratory mortality disease is high, and that's shown in the middle panel. So we wanted to examine the association between components of PM2.5 and cardiorespiratory mortality, and we did that through a county-level cross-sectional study focusing on the contiguous United States, but also using the southeastern United States as a subset for the analysis. We found that PM2.5 in the southeastern United States was associated with higher per capita mortality than for the contiguous United States. And again, that mortality was specifically cardiorespiratory mortality. We found that variability in secondary organic aerosol, as indicated by the IQR range, was associated with higher per capita cardiorespiratory mortality than PM2.5 total. And that SOA was associated with higher per capita cardiorespiratory mortality than PM2.5 on a per mass basis as well. And we found that both biogenic and anthropogenic VOC-derived SOA seem to contribute to this overall association with high cardiorespiratory mortality rates. And I'd be happy to take any questions in the chat box.
Thank you, Hala. I think our next speaker is Dr. Shukla.
Hi everyone, I'm Komal, and our study is zip code level air quality analysis in New York City. This study is sponsored by NYSERDA and is being done at UNC, ABD Associates, and New York City Department of Health and Mental Hygiene. So currently we have a lot of these tools and models which can help us estimate PM2.5 and health impacts. But the finest we can go with them is county level assessments, and these are also very computationally intensive. So here the study is trying to evolve and evaluate a novel integration of two tools with which city planners can greatly benefit and analyze the various policy options. We're trying to target PM2.5 in New York City. Here we are integrating two tools, C-Tools and Cobra. Cobra is co-benefit risk assessment tools, which is another kind of reduced form model, which can help us estimate secondary PM 2.5 concentrations. To understand PM 2.5 concentrations better in New York City, this study has produced zip code level emissions and concentrations in comparison to the previously existing grid level scales, specifically coming from CMAC. New York City has around 192 zip codes. And so this study is focusing on curating emission sources independently in these zip codes, and then health impact assessment individually at such smaller scale. The integration of C-Tools and Cobra gives us the total PM 2.5, and by reducing the PM 2.5, we calculate the health impacts. We're using NEI 2016 county level emission estimates, and we further classify them in area, road, point, and ships in transit sources, and eventually compute primary PM 2.5 concentrations at C-Tools. The primary estimates are then given to the Cobra, where it computes secondary PM 2.5, and thus the total is calculated. At NEI 2016 level, we have divided all our sources in point, roads, ships, and area, where area sources contribute to major of the emissions because of our definition of area sources, because we're counting everything in area sources except the electrical generating units. Those are counted as point sources, and then underway emissions that are counted as ships and transits, and then road emissions that comes using moves and using activity data. The integrated tool is so powerful that you can select the location in this interface, location as in a zip code, or some zip codes as in counties. New York City has 5 counties, so you can go to a level of a specific county, and then once you have selected a county or a zip code, you can modify the emission estimates, and emission estimates can be modified tier based, and then the modification of these emissions can give you the change in the impacts of health impacts. And the integrated C-Tools and Cobra tools also allows users to analyze the air quality health impacts of emission reduction or emission increase scenarios. It will also enable the users to change the PM 2.5 concentration, and thus we can visualize the incidences of mortality or morbidity that has changed due to the change of PM 2.5 concentrations. And the key takeaways that we have from our study is that PM 2.5 is specifically higher in lower Manhattan region of New York City, while it's slightly lower towards Bronx, Queens, and Staten Island. The primary PM 2.5 concentration is about 60% of the total PM 2.5 concentration. Our integration also gives us a bifurcation between the organic and inorganic components of PM 2.5. And in terms of sources, area sources contribute around 80% to the total PM 2.5 emission, followed by on-road sources, which go about 12%, and then the ships in transit and point sources. We're trying to use this tool further to finalize the integration and expand its capability to perform New York statewide assessments. Currently, we have estimated PM 2.5 concentrations at all those zip codes, and then we have identified how much mortality or specifically deaths can be avoided by reducing PM 2.5 concentration at a specific zip code. Thank you.
Thank you very much, Kamal. Our next speaker is, sorry, I did not move that along, is Alejandro Valencia.
Hi, I'm Alejandro Valencia. I'm a PhD student at UNC Chapel Hill, and we'll talk about improving emission inputs via mobile measurements to estimate fine scale black carbon concentrations to geostatistical data fusion. And so pretty much this is a follow-up work that continues our efforts published last year with Vlad Isakov here. And what we did was we combined dispersion modeling and with fixed and mobile measurements with Bayesian maximum entropy methods, data fusion methods, and used that to characterize air quality. And so our dispersion model was based on C-Tools algorithms. our observations, we used the KC Tracks field study that was based in Kansas City. You can see our domain here on in this picture here. We had a year of fixed measurements in between 2017 and 2018, but also had 31 sampling days of mobile measurements across 4 months. And so the first thing we wanted to do was take our previous efforts and improve upon that. And so we established an inverse modeling approach to adjust our most uncertain emission inputs. And so we used this inverse modeling approach that's pretty much based on ordinary least squared regression. We saw changes in our emissions that improved our performance. We then applied the BME data fusion method to create monthly spatial maps of black carbon. And so by doing this, we were able to capture the effects of months that had mobile measurements available to us and compared those without mobile measurements. And we also were able to identify elevated air pollution from local sources. In this case, we saw a big increase from warehouse sources, which are located in this very complex domain. Finally, we did cross-validation analysis to show that our model did improve by applying the inverse modeling and the data fusion. Inverse modeling improved our dispersion model by almost 50%, R squared by 50%. And doing different cross-validations of different models, we saw that by using the inverse modeling and our BME data fusion showed the best model performance.
Okay, great. Thank you very much. I think our next speaker is Robson Will. Go ahead.
Yes. I am Robson Will. I'm a master's student at Federal University of Santa Catarina. And this topic is I analyzed of the performance of the WRF model in high latitude regions of the southern hemisphere. This study analyzed the performance of the microphysics and the border layer parametrize of WRF model in 3 cities in south of Brazil in the states of Santa Catarina with different geographic conditions, one with high altitude, one in the coastal region, one in the middle of the continental region. I studied in my master the relationship between atmospheric conditions and cardiorespiratory disease throughout in the states of Santa Catarina. However, there are not meteorological data for small cities and the states and many times series in the large and medium cities are incomplete or the data is not good enough. So I analyzed the best WRF configuration for each region to guarantee the best results in my search. The errors in the search and the association measure are performed use a bias, CMAS, and correlation index, and the PICO in 4 meteorological elements: temperature, atmospheric pressure, relative humidity, and wind speed. Results for temperature show the different parameterizations are the best suited for each of the analyzed regions. The difference between the configurations are repeat for the other climatic elements, demonstrating that the use of the single parameterization is not the best option to describe the meteorological conditions on in a large scale. Requiring the divisions of each regions into smaller areas considerate the geographic factors. We found combinations of parameters that can be a reference for new studies involving atmospheric pollution, health, and meteorology in the entire high latitude regions of south of hemisphere. Thank you.
Thank you very much, Robson. Our next presentation is Matt Woody speaking about HEM4.
Yeah, thanks, Amir. Yeah, I'm Matt Woody with the US EPA. I'm going to be presenting the human exposure model version 4. Brandon talked about it a few minutes ago, but basically it's a inhalation risk exposure model that the EPA uses to assess risk from multiple air toxics, typically focusing on fine scales and single facilities or groups of facilities. It uses the air mod dispersion model at its core to estimate pollutant concentrations, and then uses those concentrations to then estimate exposures. It has built-in health reference values and census data that it uses to estimate individual risks and population risks, which include cancer risks, non-cancer risks, and chronic non-cancer risks and acute risks. And then new to HEM4, the soon-to-be released HEM4, it's finished but not available on the website yet. It's just in the process of being posted now. But some of the new features in HEM4 include that it's now usable anywhere in the U.S. Previously, it was restricted to it was restricted to the U.S. Now you can use it anywhere. That was because by default it used U.S. Census data, but now a user, if they provide receptor information, it can use that instead. There's some new graphical output options which help to analyze risks by facility, by emission type, by source, by pollutant, by risk category. That has all functionality in one tool. Previous versions of HEM, there were two versions of HEM: a single source or single facility and a multi-facility. And then there were a number of post-processing tools. Those are now sort of incorporated all into one package, one executable. And then just the final note is that it's now open source, written in Python, whereas the previous version was written in Fox Pro. And then at the bottom of the slide, you can see there's a link that'll take you to the HEM website, which, as I mentioned, HEM3 is currently at that website. But once HEM4 gets posted any day, HEM4 will be on that website. And you can also, at that same website, download MET data for approximately 800 ASOS MET stations that are used in HEM, as well as the exposure, the health reference values, and as well as the census data that's used in HEM to model at census blocks. And then the picture, the graphic you see here is just an example output from HEM, where it's showing chronic cancer risk from a single facility at census blocks, and the color coding is sort of it's scaled, so red is higher risk, yellow is moderate risk, and green is lower risk. But if that's a KMZ file, so you can actually go in and click on each one of those points and see the actual risk numbers if you're interested. So thank you.
Thank you, Matt. I think we have a speaker, Tammy Zhu. I don't know if she's here. Go ahead.
She dropped. Okay, so yeah. So let's move to the next one.
Okay, I think Tam is here. And last but not least is Shunliu Zhao. Go ahead, Shunliu.
Oh, hi. My name is Shunliu Zhao. I'm from Carleton University in Canada. My presentation is about the health benefits of reducing PM2.5, which is well known to cause health problems. We use a CMAC adjoint model to calculate the benefit per ton, or BBT, or PM2.5 primary and precursor emission reductions. The benefit is nationwide for the US, and the per ton emission reduction is at a local level or at every model grid cell. So the motivation of this work is to provide benefit per ton or BBT maps for different emissions. Amir, can you go to the next? Yes. So like the one shown on the screen, it's the BBT for primary PM2.5 emissions. So we ran the adjoint model for the year of 2016 with a 36 kilometer resolution. From what we got, we found that the BBT values have strong variations in space and time. You can say that some emissions match more than the others. We also found that in general, the BBTs for primary PM2.5 and ammonium are much larger than those for NOx and SO2. And we did some cross-model comparison. There's a recent EPA report that compares the BBTs from a few models, including CMAC, CAMAX, and several other reduced form models. So we compared our adjunct results with them. And in general, the values are comparable. We also talk about the uncertainties related to model setups that can affect the BBT values. For that purpose, we chose a 2-week episode for each season. We got some preliminary results, but it's mainly work to be done in the future. That's it. Thank you.
Thank you, Shalil. And I think that ends our overview. We have a few minutes left and a couple of outstanding questions. I think there is a question that was just answered, the question for Jim. Given the diversity of the methods and the efforts involved in each of the 7 models, are you able to give a recommendation on the approach that works best for exposure characterization for use in health risk studies? Jim, do you want to take that?
Yeah, I could take a comment. I mean, it's, of course, without having monitoring everywhere throughout the country, we can't really evaluate all these models and say there's a clear winner and all that. So it's hard to make a decisive answer. But, we did find at the national scale, like if you're doing a national risk assessment, all the models give you pretty much the same population weighted average concentration across the US. So they're all kind of similar at the national level, and one way or another, you could kind of argue to use them, leaving aside the chemical transport models that aren't constrained with observations and are a bit different. The methods that incorporate some CTM modeling like CMAC and combine that with monitors tend to do better than monitoring alone. If you just interpolate monitoring data, you miss mountains, you miss fires, and you have weird like circular artifacts. And, so there's that. A couple methods that are kind of sophisticated and have high resolution and some nice features are the Van Donkel et al. Work based on the satellite retrievals combined with Geoschem. That's a nice product. And the group at Harvard, Joel Schwartz's group, the D et al. 2019 paper that does machine learning and builds these high resolution fields. They're not without their limitations, but those are some of the nice fields out there. But their limitation is that, those are products that are made available to the public. Like I can't go run that method for my CMAC case, and probably people in the community can as well. But you can run CMAC, you can do these interpolation methods, you can run downs. So the choices you may have is in practice, you may be using a simpler operational method you could run quickly, and that gives you reasonable national scale performance. As you get into these more exotic techniques, only outside of the study authors, it's hard to apply them. And when you look at the urban areas, the kind of some of the features don't seem all that realistic or not necessarily in agreement. So a lot of the high resolution you get out of them, there's some open questions about how valuable that is. But I do like those new advanced methods, but I just wouldn't be able to run them myself. So I'd probably lean on the other methods that give you basically the same picture nationally in terms of the population weighted concentration.
Okay. I don't see any open questions. Does any of the panelists have a question? I do have a couple, but if anyone else has a question, and we have 3-4 minutes left. So maybe one question for Michael and Track My Air. Do you see this tool being used to give statistical or stochastic nature to exposure estimates in EPI models?
Right now, it's a deterministic model, so it gives you a point estimate. We could always add in some type of probabilistic output, but right now it's for an individual, and we could do some type of parameter bounds and running a Monte Carlo simulation, but right now it's currently just giving you point estimates based on a deterministic approach. It kind of complements EPA SHEDS approach, which gives you population level estimates.
Okay. Thank you. Any other question? Well, we have 2 minutes left at the. Okay, we have a question from for Halda. Since the inorganics such as sulfate, nitrate, and ammonium are also contributing considerably to the total PM, what could be the effect on mortality combined inorganics over the Southeast U.S.?
Thanks for the question.
1 minute.
Yeah, so in our modeling, we used a variety of single pollutant and multi-pollutant models. So we included sulfate, nitrate, and ammonium in all of those techniques. We found that sulfate was positively associated with mortality, but not to the same degree as secondary organic aerosol across the United States. No significant association of sulfate with mortality for the southeastern United States. And then ammonium nitrate also was showing some association with mortality, but it was not as strong as secondary organic aerosol. So it's not that the other components don't matter. We just see secondary organic aerosol being much more strongly associated with cardiorespiratory mortality. And on a per unit mass basis, it's also more strongly associated than the other components.
Thank you for the answer, Hamla. I think we are at the end of our time. Unless there's a burning question, I just want to thank both my co-chair, Dr. Isakov, and also all the presenters and also the attendees for joining us. Thank you very much.
Thanks, everybody.